Excellent, that's what we want to hear.
Yes, sir.
Okay, so let me see. Yeah, well, let's kind of start right in. Does anybody have anything before we get ourselves started? Okay. Well, one thing I noticed, I want to do an example similar to I want to talk more about that last example we were doing last class. I will admit to you, by the way, do you guys find those notes I post helpful?
Yes.
Yes.
Yes, okay,
Yes.
okay then.
10 out of 10.
I figure my handwriting is bad enough that you have to deal with it, but, so with that said, last class, we were working a problem at the very end, and it was like so close to the punchline. And when I got back to my office, I was like, I just can't do it. And so I took the liberty of adding the punchline to the bottom of the last page of notes. Okay? So there's a little bit online, this last bit is we didn't get a chance to talk about last class. We'll do another example and talk about it. But I just wanted to let you know, because you guys are used to, this is exactly what we talked about, and I took the liberty to add a couple sentences this time. Okay, and so let's talk more about that, and hopefully this will be quick, I think, and then the goal is to get into our next chapter today. But is that a hand?
Yes, I just had a question about this because we often use cards as an example here, especially for sequential without replacement.
Yeah.
Because if you're dealing 5 cards,
and
there's 52 cards in a deck,
it's
5 to the power of 52 possible combinations. Or is it not that, because when you deal out a card, that card's not in the deck anymore? So
it depends on if the order of your selection matters or not. It depends on if you're playing blackjack where it matters, then that leads you to a sequential approach. If it's like poker, which I don't play because I'm a statistician, okay, right? But if it's like poker where the first thing you do is reorder the cards, then that would be a combinations thing.
Okay.
Right. And so, actually, let's talk about that, okay? And so, just as a recall, NCX is n factorial over x factorial and minus x factorial. This is combinations. Okay, and one of the big things right toward the end of class we were talking about, one of the tools it's used for is for counting subsets. Okay, and let's talk specifically about that replacement, selection without replacement.
In a hand of cards, if you get dealt the ace of hearts, there is a 100% chance the next card will not be the ace of hearts.
That would be true.
Unless they're cheating.
Right? Selection without replacement. And in particular, I'm thinking about when the pool you're choosing from is relatively small, so those changes in probability are significant, That's why cards come up a lot, And so, but it's also more than that, cards are just pseudonyms for many things, right? For instance, you buy a case of parts, right? It has 25 parts in it. Well, usually there's some sort of sampling plan to check them. You probably don't check all 25. You probably randomly pick like 5 of them and see based on that, right, whether it's a conforming lot or not, And so selection without replacement, okay? First off, everything we had done until yesterday was creating a sequential approach. sequential approach. I think I spelled sequential wrong. Maybe it's not. Sequential approach. And this is order matters. Okay. And by the way, I'm trying to avoid using the word, but if you've had a discrete math course, when I'm saying the sequential approach and order matters, what I'm talking about is permutations, okay? You know, and so, you know, for instance, and again, use that same example. We pick 3 cards from a deck, and we should get away from cards apparently, but 3 cards from a deck of 52 without replacement. Right? Find the probability that how many of them that two of them are hearts. Right? And we saw then in the sequential approach, you have to consider all the orderings. And the upshot of this is that this sequential approach gets nasty fast, right? And so for instance, the probability of 2 hearts is the probability of heart, not heart. I should draw not heart with an X through it. Okay. Plus the probability of heart, not heart, right? Plus the probability of not heart followed by 2 hearts. And we did convince ourselves last time there are 13 hearts in the deck, 39 non-hearts. That would be 3 times, what did I say? 13 times 12 times 39 over 52, 51, 50, right? By the way, we can work through those details if you want to work through those details. I'm kind of feeling we've done a lot of these problems, okay? But the deal is needing to map out all the possibilities, right? It gets to be too much pretty fast. It's too much fairly fast, okay? And so maybe there's another way, and there is another way, and the other way is to, rather than think about it as sequences, think about it as sets, in particular subsets. Don't forget, in a set, all it means is you belong to the set or you don't belong to the set, and within the set, order doesn't matter, right? And so, and you'll also notice in here, there's nothing in here implying an order of those hearts, right? And so the other approach is taking a set approach. A set formation approach. Right? And so consider that the pool of 52 cards, right? And if I'm randomly choosing from this deck, if we're randomly choosing from the deck, right? What's each subset of size, whatever we call it, little n, right, is equally likely, right? All the subsets are equally likely. You might get these 3 cards, you might get those 3 cards, right? right? The chances of getting three cards with a 1, 2, 3 in it are the same as the probability of 3 cards with a 4, 5, 6 in it, right? And so each subset of size n is equally likely, right? Thus, the probability that a subset of size n has a particular trait, is simply the number of subsets of size n, with that trait divided by the total number of subsets of a size n. Right? And so if it, and so kind of, do you see the distinction between taking this sequential order matters approach versus this approach over here where you're simply collecting subsets, right? So to answer this question we posed to start with, how did we start this, right? Pick 3 cards from a 52 card deck. What's the probability that 2 of them are hearts, right? And so we revisit the last example, right? The probability that a random 3-card hand has 2 hearts, right, is, right, the number of 3-card hands that have 2 hearts in it divided by the total number of 3-card hands, right? Number of 3-card hands with 2 hearts divided by the total number of 3-card hands. Does that make sense? You know, right? And if you like that, I'll change colors here. Okay, maybe I should just keep writing on the bottom there. Where's the top? There it is. Okay, so looking at that same problem, the total number of 3-card hands from a 52-card deck, right, is how many 3-card hands can be created from a 52-card deck?
So this was the question that I had about this.
Yeah.
Because when we do our usual 3 to the power of 52, that implies that 52 to the power of number of spaces to the power of number of options.
Not without
replacement.
replacement, right? If order matters, there's 52 times 51 times 50,
Yeah.
using the multiplication rule. But if order doesn't matter, how many are there?
52 choose 3. No?
52 choose 3. Yeah, exactly right. Is 52 choose 3, right? Choose 3 of the 52 cards, right? Yes. Don't forget now, order doesn't matter here, right? And so, now, how many 3-card hands have 2 hearts in them? Right? now, okay? And again, order doesn't matter, right? But it's the ways you can pick two of the 13 hearts, right? Times, because it's that multi-stage multiplication rule, times the number of ways you can pick one of the non-hearts, right? Right? Ways you can pick one of the non-hearts. You see what I'm saying there? Right? And how many ways are there to pick 2 of the 13 hearts? There are 13. Choose 2 ways to do it, right? You can form, that's how many subsets of size, that's how many subsets of size 2 could be created from those 13 hearts, right? 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 And what is that? What is 13 times 6? 78 is what I think that combination turns out to be. And similarly, how many ways can you choose one of those, one of the 39 non-hearts?
Take what you said, strike that, reverse it. 39 choose 1.
39 choose 1, right? And 39 choose 1 is what number? Quickly in our head.
Not 1.
It's 39, right? Right? You got 39 non-hearts there. What's the one that, you got 39 choices for what that non-heart is, right? Right? And so the probability of 2 hearts, right, is 13 choose 2 times 39 choose 1 all over 52 choose 3. Right? Let's see. That denominator, let's see. 13 choose 2 is 13 times 12 divided by 2, right? 13 times 6 is 13 times 10 plus 8 is, what am I trying to do here? 13 times 6, I think, is 78. Am I right?
78, yeah.
78. By the way, anybody, don't let me do anything in my head. Anything I do in my head is not trustworthy, right? Did I get that combination right?
I believe so.
13 times choose 2?
Yeah.
Yeah. By the way, do you know the trick of that? They're not hard, right? Why? Well, how did I do that so quickly? 13 choose 2 is 13 factorial over 2 factorial times what?
Is it 11?
11 factorial. 11 factorial. Okay. 13 factorial is 13 times 12 times 11, 10, 9, 8. In other words, 11 factorial, right? 11 factorial. By the way, what's 2 factorial?
Just 2.
2. Okay, 2 times 1, right?
0.
Over 11 factorial. The 11 factorials cancel out. That's where I was getting 13 times 6.
Cool.
Okay? So there's a couple patterns in there. By the way, you also know that if n choose 2 is n times n minus 1 divided by 2, right? Isn't n choose n minus 2 the same number? Right? Due to that symmetry, right? So notice also that would be equal to 13 choose 11, right? And so anyways, what did I get there? 78. Okay. And 39 choose 1 is 39, okay. And 59 choose 3, well, that's gonna be something like 52 times 51 times 50 divided by 6, right? 52 factorial 3 factorial, 49 factorial, right? And don't forget, everything from 49 down will cancel out in numerator to denominator. That's where I got that 52 times 51 times 50, right? And so this little piece, I'll tell you what that is 52 times 51 times 50, close it, and let's divide that by 6. 22,100, right? That probability is 78 times 39 divided by 22,100 is about 0.138. Okay, so there's about a 14% chance that a 3-card hand will have 2 hearts in it. Make sense? Make sense? Okay. Okay. Right. And so do you see these two kind of competing strategies, right? Right? Yeah. Now this one here is actually fairly versatile, right? Right? So for instance, how many 4-card hands have one of each suit? And it definitely sounds like I upped the game since you can't even read it, right? Right. But seems like I really upped the game there with this question, but I actually didn't, right? And don't forget that every 4-card hand is equally likely to be the one that you receive, right? So again, it's simply the number of hands that have this trait divided by the number of total hands there are there, right? And so the probability of one of each suit, right, is the number of 4-card hands with one of each suit, right, divided by the total number of 4-card hands. So how about that numerator? The denominator, I think all of you guys would, if you've been listening here and liked that first example, would readily say, well, if there are 52 cards, there must be 52 choose 4-card hands, right? Yeah?
So this would, the numerator would be 13 choose 1 times 4?
Yep. How many, so in other words, and let's put a reason behind that, right? You have to, it's the number of ways to pick one of the 13 hearts times the number of ways to pick one of the 13 diamonds, right? You know what I'm doing here, times the number of ways to pick one of the 13 clubs, okay, and ways to pick one of the 13 spades, right? Do you like that as the numerator? You see what I mean? And each one of his 4 times came from what are each one of these? 13 choose 1. 13 choose 1 is just 13, right? Divided by the total number of ways to pick 4 from a 52-card deck, right? Or in other words, simply, right? 13 choose 1, 13 choose 1, 13 choose 1, 13 choose 1, all divided by 52 choose 4. Feel okay? Right? I don't know what that is, okay? I know the numerator is 4 times 13. The denominator, I bet there's a lot of these. 52 math probability down to NCR 4. 27, 0, 725. So approximately, let's see, put it in the denominator times 20. Is that 52 in the numerator? It's a pretty small number. 0.00019 or so. Yeah. How's that feel? Does that seem okay for us? Yeah.
So, in this example with the deck of cards, replacement does matter, which changes how you calculate the denominator.
It changes everything about the problem if you're doing it with or without replacement.
Okay,
Because don't forget, if you're doing it with, if you're putting the card back again, they're independent,
okay.
right? How's that feel? Does that feel okay for us? Yeah. Isn't what's a flush? A flush is where they're all the same suit, right?
5 cards, yeah.
Yeah, but let's do it with 4. Well, we can do it with 5 cards. Let's do it with 5 cards. So if we're dealt 5 cards, what's the probability they're all the same suit?
Over the number of 5 cards, yes.
Or this is how many 4-card hands have one of each suit, or I mean, what's the probability? What's the probability of a 4-card hand having one of each suit? Okay. Well, one more of these, then we'll maybe move on, but and I really should be branching out from just cards and things like that. By the way, what we're talking about, this you kind of alluded to it before, this very often comes up in quality control in sample theory, right? You purchase X number of components, you have to validate whether you're going to accept the lot or send it back again. You're not going to inspect all of them, right? But you see that as you're inspecting, it's without replacement, since you're not going to inspect the same part twice. You know what I mean? So that's very often where something like this comes up. In fact, a good exercise would be something like a case of 20 parts has 3 bad parts in it. If I sample, vary the number, 3, 4, 5, 6 of them, what's the probability of getting a bad part? You know what I mean? And so, let's see, let's do this full house with this, what was it called, a flush? Okay. What's the probability of a 5-card flush? Right? All 5 cards are the same suit. Okay. So, the probability of a flush, I'll start us out, would be simply the number of 5-card hands that all have the same suit. Number of 5-card hands that have all the same suit, divided by the number of 5-card hands. Okay. Yeah. Huh. So what do you think for this one? What do you think for this one? I heard some suggestions before. Those same suggestions are still valid. What do you think?
I think it's 13 choose 1 times 12 choose 1 times 11 choose 1 times 10 choose 1 over.
You're ordering. You're ordering, right? All you want is a subset, right? For instance, all 5 might be hearts, right? In which case, which can be done in 13 choose 5 ways, right? But I kind of gave the money away right there when I said that was a hand of all hearts, right?
Would it be 4 times 13?
4 times, right? Because when we say the flush, that's the probability that they're all hearts, plus the probability they're all diamonds, right? Plus the probability they're all clubs, right? Last but not least, the probability they're all spades, right? Something like that. So that's where that 4 times is coming from, right? So this whole thing becomes equal to 4 times, to pick the suit there, right? 4 times, what am I saying here? 13 choose 5 divided by 52 choose 5. You see what I mean? And you know, whatever, but think about trying to do either of these problems if you are trying to deal with the sequences, right? That might be a whole different ballgame, right? And so, I don't know what this turns out to. Let's see. I'll tell you. We got 4 times parentheses 13 math probability CR5, close it again. So that numerator at least is 5148. The denominator, how many 52 card hands are there? We've probably computed this a time or two. 5, oh, that's a big number. 2, 5, 9, 8, 9, 6, right? Times 5148, and there's about a 2% chance of a flush. Right. How's that feel? Does that seem okay for us? Just in general?
I can't believe that we can do math and figure this out.
Right. So you know, and so you see how actually powerful this is.
Yeah.
You know, and well, let's be honest. History of probability. How or why did probability even begin? This is why it began, right? It began, I want to say the first real probability model was developed, I think it was in England, and the intention was to quantify games of chance like this, right? You know? Okay, good. And so, yes. And I know that we only really looked at decks of cards, but these models, you know, so for instance, I read a paper once, okay, where they wanted to estimate the number of fish in a particular small pond, right? And so what they did was they, you know, and that's probably a fairly small number, so selection without replacement probably matters. So you're looking at something like this. So what did they do is they caught a bunch of fish, put a tag on them, right? Let them circulate back in the pond, right? And then after they were well percolated through the pond again, they did another catch, and then they calculated the proportion of the second sample that were tagged, and from that they could extrapolate what the pool number was, you know, and that was coming from this particular model. This particular model, where you have it broken down into simple 2 cases, like our very first exam, well, that's not even one either. We doing? Yes, yes, yes. This example right here, it actually has a name. It's known as the hypergeometric. Okay. Yeah.
So I guess my hang up with replacement and not is when we launched into this, our example that got us into this was 4 trials with successes and failures. Trials are independent.
Mm-hmm.
And we needed to find the number of trials to give you exactly 2
Different
successes.
application.
Okay.
Different application. That in that particular application where you've got the independent trials and you're trying to count the branches, n choose x provides those number of branches. This is set formation. Different application. Yeah. 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 Right. Right.
Up until this point, have the examples been mostly independent? It seems like we haven't really.
It's about
dabbled much-
50-50.
Okay.
About
Okay.
50-50. Okay.
Does without replacement mean dependent?
If you're, yes.
Okay.
Yes, because when you're in general, because don't forget, well, no, let's take that right. Without replacement, right?
Right.
If without replacement implies you pull something from the pool and you do not return it.
Yes.
Doesn't that change the probabilities of what's left in the pool?
Yes.
Dependent.
Okay.
Right? What happens if you take something out of that pool, look at it, write it down, and put it back in the pool and pick again? Are those dependent or independent?
Independent.
Independent.
Just want to make sure
Right.
I'm getting that
Right.
like vocabulary correct. I wasn't sure if dependent like might mean something other than without replacement in different contexts.
Dependent means the probability of one event affects the probability of another event.
Okay.
Right?
Cool.
Right? And so, replacement or not replacement is an example of that. Yeah.
Thank you.
All right, all right. So, whew, what do you think? Chapter 1, done?
Chapter, this is just chapter 1?
Chapter 1.
Done, not dusted.
So, let's see. Good job, by the way. Good job. So let's shift gears. Okay. And this is gonna seem like a big shift, but it's actually not. It's out of hand.
Yes, it is a hand, and this is not about going in depth anymore. As far as the midterm, is the end of chapter 1 the cutoff of what will be at the midterm?
The end of today's conversation.
Okay,
Okay? Midterm is next Wednesday, right?
yep.
Everybody's on board there next Wednesday, right? So I don't want to do new material on Monday and then ask you about it on Wednesday.
Okay.
But everything through today is fair game.
Thank you.
Okay? Okay. So, let's see. Yeah. Well, so we want to change gears a little bit, and as I said, we want to start talking about what's called random variables. The bottom line is, to be perfectly honest, I've been using random variables since day 1. It's almost hard to not use them, right? And random variables are simply nothing more than a different way to describe events. Okay? And I think if there are any hang-ups with random variables, I don't know. It has more to do perhaps with the notation, And so let's start talking about random variables. And in our skyscraper that we're building here called probability, I don't know if I mentioned it much in this course, but usually I kind of start out by saying one of the things about probability is we build these layers on top of things, right? The foundation of probability is the sample space, right? And then on top of that, we build the notion of events. And then on top of that, we build the function from the events to the probability functions, right? So we're simply adding another layer in there, okay? So a random variable, where are some notes? Let's try to follow some notes today. A random variable, usually we give it a capital letter like X, okay? Assigns to each outcome, a number. Okay? Okay. So by the way, every time I said something like let's flip a coin 5 times, what's the probability of 3 heads? Right? I'm referring to a random variable, right? Right? And so more to the point, it is a mapping from the sample space to the reals. Okay? Okay? And so, and another way to think about it is it forces or creates a partition of the sample space, right? Based on the number. Okay? Okay? Now, so for instance, right? Example, right? Let's, simple, let's, whatever. Toss a coin 5 times. Let X equal the number of times it lands on heads. You'll notice that, right? So now all I'm doing is codifying numerically each outcome, right? For instance, the outcome tail would be X is equal to 0, right? Right? Or the outcome head tail would be X is equal to 1, right? So you see how we're simply codifying those, right? Right? You'll notice that the range of X in this case is 0, 1, 2, 3, 4, or 5. Right? We could toss a coin repeatedly. Let random variable y denote the number of tosses until and including the first success, the first head is obtained. Okay. Here we see the range. This is a different random variable. Okay. And we see here that the range is, what is it, right? 1, 2, 3, 4, ... Right? Range of y is 1, 2, 3, 4, ... Does that make sense? Right. By the way, these are both examples that we've kind of explored. In fact, we can all compute the probability of both of those, of these, right? This first one is an example of what's called a binomial random variable. This second one is an example of what's known as a geometric random variable, right? And if the range of a random variable is either finite or countably infinite, that random variable is called discrete, okay? If the range of a random variable, by the way, get used to me, whoops, well, you can't get used to me yet, there you go. I always use RV to stand for random variables, okay? Okay? If the range of a random variable is either finite or countably infinite, then that random variable is called discrete. Okay? If the range of a random variable is an interval of real numbers, right? For instance, let x equal the time to complete a task, right? Right? If the range of a random variable, okay, is an interval of real numbers, right, such as let x equal the time for a random person to, to do a task, such as complete an assembly or something like that, right? All right? Then that random variable is called continuous. Continuous. Okay? Okay. And by the way, I didn't erase it. For instance, here is an example of a continuous random variable. Right here. Yes, please.
We're calling it a variable, but I see you're using function notation.
You know, that's where it gets to where I kind of qualified this by we're not really reinventing the wheel, but a lot of it is in the notation we use, because our notation, like nobody says the range of a random variable, right? What we do say is what values can this random variable take on? You know what I mean? And so even though it is indeed a function, it is a mapping from the sample space to the reals, to the numbers, that notation typically doesn't get written. For instance, you'll see notation such as calculate the probability x is equal to 2. And so. Okay. How's that feel? And so if now let's add another layer. So we've gone from the sample space, now we've gone to this, from the sample space to this next level up called random variables, where they are nothing more than codifying your outcomes numerically. Okay? Now let's add a layer on top of that, a probability function. Okay? Associated with a random variable maybe is a probability function. Okay. Good, good. A probability function, and a probability function is a mapping from the random variable to the reals. And in fact, the range of any probability function is the closed interval 0 to 1. Okay? Okay? Let's talk a little bit about that. Now, so we introduced this notion of a discrete random variable and a continuous random variable. Okay? I will tell you in our book, Chapter 2 is discrete random variables. Chapter 3 is continuous random variables. If you have a discrete random variable, don't forget, that means the possibilities are either finite or countable, right? Countable means listable. Listable means identifiable, right? So for a discrete random variable, probability questions become summation problems, right? Right? If you're rolling a dice 5 times and you're whatever, or a coin 5 times and x is the number of heads, the probability x is bigger than 3 is the probability it's 4 plus the probability it's 5. It's a summation problem, right? If x is continuous, then you can't list the values, which means you cannot isolate them, which means you can't add them up, and it becomes an integration problem. Okay? Okay? And so, let's talk about a discrete random variable. I brought more paper. Might be a short class. Discrete random variables. Okay. Okay. And that's when the possible, it's when random variable x has a finite or countable set of possibilities. Okay, okay, good, good. Let's see. Then, the probability function. The probability function. Right? For a discrete random variable, a lot of books refer to the probability function as a probability mass function, okay? I do know software and calculators don't really conform to that very well, okay? But for a discrete random variable, it's often referred to as a probability mass function. And so if you've seen PMF, that's where that's coming from, okay? And we'll denote it as P subscript the name of your random variable, okay? It's a function of an input, and that input is one of the values that random variable can take on, okay? Okay? This is one of the values that random variable can take on. Okay? Let's do, I know it's a trivial example, and well, maybe let's maybe make it a little less trivial. Okay, let's see. Oh, it's almost that time. How's this feeling so far? Is it almost time for us to take a little break? Let's take a little break. We'll come back. We'll try to wrap our heads around a little example of this so we kind of see what's going on here. Okay? Yeah. Let's take about 10 minutes and then what, about 25 of or so? Sound good?
Cool, thank you.
Okay.